Now, our pacemaker cells, as I've said, make up 1% of our cardiac muscle cells. And we have three populations of these that make up what we call the cardiac conduction system. And this is responsible for generating the action potentials. So it sets the pace of the heart. And depolarization in the pacemaker cells is going to happen more slowly because you don't have voltage-gated sodium ion channels in the pacemaker cells sarcolemma. They also don't have a plateau phase. And so the membrane potential oscillates like what I've drawn there. It remains at resting level and it occurs kind of in a cycle. And that is because of non-specific cation channels that pacemaker cells have that no other cells do. They have a slow initial depolarization, and the pacemaker potential starts with the plasma membrane being hyperpolarized. And so that will open these non-specific cation channels in the membrane, and sodium ions can begin to leak into the cell and potassium ions can start to leak out. So it's a very slow depolarization until it reaches threshold. And when it reaches threshold, it goes into full depolarization, where all the voltage-gated calcium ion channels open, and the calcium ions come into the cell, and that fully depolarizes the sarcolemma. Then the repolarization, remember our calcium ion channels, they close at a specific time, regardless of whether they are ready to close or not. They close, and when they close at the very same time, the voltage-gated potassium ion channels start opening, and potassium starts leaving the cell, and so the membrane begins to repolarize. There's a minimum potential phase where the potassium ion channels are going to stay open, and it's going to reach its minimum potential. And that's when the membrane is hyperpolarized and those non-specific cation channels open and all this starts over. So you can see here, this orange one represents the non-specific cation channel. So this is slow depolarization, okay? You've got more cations that are going to leak in than leak out. And that causes the membrane to slowly start to depolarize and move towards threshold. And once it reaches threshold, the calcium ion channels open and the calcium moves in, and that causes full depolarization. Then the nonspecific cation channels are closed, the calcium ion channels close, and the voltage-gated potassium ion channels open, and potassium starts to flow out, and that causes repolarization. And then, with the potassium ion channels moving out, the nonspecific cation channels are activated again, and so the membrane repolarizes, and the cycle repeats. Now there's three populations of pacemaker cells that make up this cardiac conduction system. There's the first is the sinoatrial node, or for short we call it SA node. And it's in the upper right atrium, and it's inferior and lateral to the opening of the superior vena cava. And normally, the SA node is going to depolarize faster, about 60 or more times a minute. And this is going to be influenced by whether it's parasympathetic or sympathetic nervous system stimulation. Now, then the second population is the atrioventricular node, or AV node. And this is posterior and medial to the tricuspid valve. And it depolarizes slower than the SA node. So it's only going to depolarize and generate about 40 action potentials a minute. So SA node is 60, and then it slows down at the AV node. And then the slowest group makes up the third population of pacemaker cells, and that would be the Purkinje fiber system. And these depolarize even slower at 20 times a minute. So it's going to slow down as it moves through these three populations. The Purkinje fiber system includes the atrioventricular bundle, or the AV bundle, and that penetrates through the fiber skeleton of the heart and goes into the inner atrial septum and the top part of the interventricular septum. And then the right and left bundle branches go on down both sides, the right and the left, of that interventricular septum, and the terminal branches come up around the other sides and kind of penetrate through the ventricles. So you start up in the SA node is found up, sorry, I went the wrong way. SA node is here. It's going to generate about 60 action potentials, and you see how the fibers extend through the, reaching all the cardiac muscle cells in the right atrium and the left atrium. And then it moves to the AV node, and here it slows down to about 40 action potentials a minute, and that gives time for the blood to flow through the atria and get to the ventricles. Okay, then it moves into the third system, which is the Purkinje fiber population of cells, and it's got this AV bundle here, and then the bundle branches going down the inner atrial septum and the top part all the way down both sides of the interventricular septum, and then the terminal branches are going to penetrate through the ventricles and stimulate all the cardiac muscle cells there, and it's only going to generate about 20 action potentials a minute. The SA node is what we call the pacemaker of your heart, and it generates these electrical rhythms that are called sinus rhythms. And normally it generates an action potential, and it spreads to the nearby atrial cells in both of the atria. Then the AV node and the Purkinje fiber system are going to pick it up, and if the SA node's not working, the AV node will set the pace of the heart, even though it's much slower. An electrocardiogram, or EKG is what we call it here, or ECG is technically correct. The K is from German words. This is how we can examine the electrical activity in the cardiac muscle cells. And they put electrodes on the surface of your skin. You have 6 on your chest and 2 on each of your extremities. And it shows waves or deflections that show changes in electrical activity. And you can detect easily if there's any disturbance or arrhythmia or dysrhythmia, if the rhythm of the heart is not what it needs to be. There are 5 waves in an EKG, and it shows depolarization and repolarization of different parts of the heart. The initial P wave is very small, and it shows depolarization of all the contractile cells within both of the atria. And so it's just a small upward deflection. Then you have this large QRS complex that shows the ventricles depolarizing, and it has 3 separate waves, Q, R, and S. And Q is going to be the first downward deflection, and then R is a large upward deflection, S is a downward deflection. And then you have a very small T wave that is when the ventricles repolarize. So it's an upward deflection, but it's not huge. You can see here, here's the P when the atria depolarize, and then Q, R, S, that's when the ventricles depolarize, but notice over here it tells us it masks the repolarization of the atria. So the atria depolarize here and they repolarize here, but we don't see the repolarization of the atria. And then after the QRS, you have this little deflection, the T wave, where the ventricles repolarize.